Kinetic molecular theory. Yeah, there it is. Kinetic molecular theory. We've been talking about gas laws. Remember that a law describes what happens. If the pressure and the volume are this, and the number of moles, we can figure out the temperature, etc. A theory or a model explains why. Why is it like that? And so we're going to study the kinetic molecular theory of gases. This is the simplest model of behavior for gases. The gas is modeled as a collection of particles. Those could be atoms or molecules, depending on what the gas is. And those particles are in constant motion. So here we have an illustration of a flask containing a gas. And we've got these particles. These lines are just indicating their motion. So they're going like this, and they're going like that. And this one bumped into the container, and these two guys ran into each other. It's a little bit like three-dimensional billiards. That's kind of how I imagine these, because gas molecules behave a lot like balls on a pool table do.
So when they collide like that, does it produce energy?
We'll talk about that, what happens when they collide. So the first idea in the kinetic molecular theory is that the size of a gas particle is negligibly small. What that means is it's so small relative to the size of the whole gas that we can just neglect it, neglige it, right? So we can neglect the size because it just really doesn't matter. So here's an analogy with people. I think I mentioned this one before, but so the elevator here in the building, it's not really very big, but I think you could probably squeeze 10 people in there. So if you had 10 kindergartners in there, or 10 of the linebackers from the Fresno City College football team, would it matter how big those people were in that small elevator? Yeah, it would matter a lot. I think you'd have a hard time getting 10 linebackers in there unless you stack them up vertically or something. It's a small space. So now let's think about the state of Wyoming. The state of Wyoming is a fairly large state. It's not like Rhode Island or something. You know what the population of Wyoming is? 10. Close. It's about the size of Fresno. 500,000 in the whole state. So if all the people in Wyoming were really slim and fit, or if they were all couch potatoes and just really big, would it really matter to them in terms of space in the state? No, because the size of the people compared to the size of the whole state is negligent. I'm having trouble with that word. Negligible. It doesn't matter. In a smaller space where the particles are close together, such as in a solid or a liquid, the size of the particles matters, but it doesn't in a gas.
Can you compress a gas into a solid?
You can compress a gas into a solid, yes.
But once you release it, will it return back to the gaseous state?
Most likely, yes. Yeah. And we'll look at some curves relating those things later. So there's lots of empty space between the particles, and so the size of the particles doesn't matter. At standard temperature and pressure, argon atoms occupy only 0.01% of the volume. That's a very small amount. What is the rest of the volume of the gas? It's nothing. It's not nothing in the sense that the air in this room is nothing. It's literally nothing. Okay? If an argon was the size of a golf ball, its nearest neighbor would be 4 feet away. In solids and liquids, the particles are touchingly close. Okay? They're very close together. But in a gas, there's a lot of empty space. And so that's really important.
How do you get just one type of gas? Like when you say there's literally nothing else, then how do you get nothing else?
How do you get just one kind of gas? One way is by a chemical reaction. But there are also ways of separating gases. You can, there's argon gas in the atmosphere, in the air that we're breathing. There's oxygen in the air, there's nitrogen in the air, and it's possible to separate those. It's not necessarily simple, but it can be done. So, kinetic energy. The average kinetic energy of the gas particles is directly proportional to the temperature of the gas in kelvins. So, temperature, we said earlier, is a measure of average kinetic energy of particles. What's interesting about the gas is that average kinetic energy and the temperature in kelvins are directly proportional. If you double the Kelvin temperature, you double the kinetic energy of the gases. It's important to recognize that we're talking about average kinetic energy. That does not mean that all of the particles have the same kinetic energy, but there's an average. And if you double the temperature, you double the average. But there's still a range of temperatures. A range of speeds. Go back again, range of kinetic energies. I'm getting ahead of myself. When the particles collide with each other, it's a completely elastic collision. And what we mean by that is that in an elastic collision, you can exchange energy, but no energy is lost. The kinetic energy is maintained. So here's a picture. When you hit pool balls, billiard balls, and so here this orange and white ball has been hit at the green ball. The green ball was moving, and this was moving too, and when they collide, they bounce off of each other, and they continue moving. If you hit a pool ball at a stationary ball, that ball will often transfer most of its kinetic energy to the other ball, and you'll see the ball that was sitting still shoot off, and the ball that you hit at it is just kind of dribbling along. But the overall kinetic energy is approximately the same. It's not perfect because there's also friction involved on a pool table. If you do this with lumps of clay that are soft and you roll them at each other, they're just going to go funk and stick together. And all of that kinetic energy that they had from motion is going to be dissipated as heat. That's an inelastic collision. So elastic collision is like billiard balls or marbles or something where they bounce off of each other. Any questions? Yes?
So can you say that the kinetic molecular energy is just like the Charles Law with the volume and temperatures?
We'll get to the relationship with Charles' Law.
So are gases acting in a frictionless environment?
Gases are acting in a frictionless environment because there's nothing for them to have friction against.
But like a table or something, I mean.
What about a table? Well, they're not on the table.
But I mean,
They'll bounce off the table, but when they do so, it's elastic. So, I mean, this is kind of hard to get our minds around because in this macroscopic world, this world that we can see with our eyes, there's friction involved in all kinds of things, right? Why can't you throw a baseball farther? There's friction in the air, right? That's because you're having to go through the gas particles in the air. The gas particles themselves have nothing to go through. And so they don't have any friction. So, in my fantasy world, chemistry land, I think of gases as being a lot like that old Pong game. You guys might be too young to even know what Pong was. It was like one of the original computer game, right? And you had a little paddle at the bottom, and this blip would travel, right? And then you had to hit it. But sometimes you could get your paddle in just the right place, and it would just bounce around, and you could go eat lunch and come back, and it's still going, right? It never slowed down. It was computer generated. It didn't have any friction or anything, right? It'll just go on forever. That's what gas particles do. They travel through empty space, and they do not lose any kinetic energy when they're doing that. So you think about outer space, you know, if you send a projectile off in outer space, does it slow down after a while due to friction or gravity? Not unless it encounters some of the very, very widely spaced objects that are up there. It'll just keep going because there's no friction. There's nothing for friction.
I thought gravity might slow down if it's the right angle or something.
Well, if it got close enough to a planet or something large, then gravity would affect it, but the likelihood of that is pretty small. It's going to go on for a really long time before it gets to anything, right? There's no air in space. It's empty, right? It's kind of hard to think about because we don't experience that on Earth. I mean, because it looks like there's nothing in the air, you know, above the desks and stuff, and yet there's air. Air will give friction, yeah. Because otherwise, why does your hair blow black when you're riding a bicycle, if your hair's long enough to do that?
When gases are flammable, I mean, are they, and they're releasing heat at that point?
Well, they're having a reaction then.
Okay.
That would be a flammable gas releasing heat is a chemical reaction.
And that's the only time
And-
you can get them to collide, basically? Or?
Well, no, they will run into each other. They're bumping into each other all the time. But they don't necessarily react.
Static at that point then?
Pardon me?
They wouldn't be static then if they were...
No, when they react, they will form new particles, and the energy that's given off, say from the combustion of methane, that energy comes from energy that was stored in the chemical bonds. It does not come from the motion of the particles. Yeah. So gas pressure can be explained by kinetic molecular theory. Here KMT just is an abbreviation for kinetic molecular theory. So the gas particles are constantly moving. They're going to just move in a straight line until they run into something. So gas particles must be colliding with the walls of whatever container they're in. When they do that, they strike with a certain amount of force, and that force is related to how big they are and how fast they're moving. So one teeny tiny gas molecule, say running into the chalkboard, that's not going to be a very large force, is it? But it's going to happen over and over and over again. And so that adds up after a while. You know, you get somebody pokes you in the arm once, and you're like, yeah, no big deal. But if they stand there and they just keep poking you, right? It's like, wow, this is really annoying, and then your arm starts to get sore. And so even little teeny tiny things will add up. So there's all these teeny tiny gas particles running into the walls of the container. Each of them is a very tiny force, but collectively it gives rise to the gas pressure.
I know that changes with temperature and everything, but about how fast is the gas particle moving?
We will look at that. We're going to look at that. How fast gas molecules are moving. So remember that pressure is the force with which something hits divided by the area. So, you know, if you hit something with the palm of your hand outstretched, that's a force, but it's distributed over a wider area. If you hit with, say, a pin, a sharp pin where the end is really pointy, that's going to hurt a lot more, right, than if someone just whacked you on the back with the palm of their hand.
Window break.
Pardon me?
Like a window break.
Yeah, like a window break. So the same force over a smaller area is a higher pressure. So it's important to understand this relationship between pressure, force, and area. We're not going to do any problems with that, but just to realize that if you increase the area, then the pressure goes down. And this is the whole idea behind how people can lay on beds of nails and things like that, because you spread it out over a larger area. So we can explain some of the gas laws using kinetic molecular theory. So in Boyles Law, we learned that the volume of a gas is inversely proportional to the pressure of the gas. If you increase the pressure, the only way you can accomplish that is the volume decreases. It's easier to think about if you think about changing the volume. Decrease the volume, pressure goes up. Increase the volume, pressure goes down. So here we have an illustration of a container where we can change the volume. So here are these gas particles, and they're just going along, running in straight lines till they bump into things, and then they're bouncing off and going in the opposite direction. If we make this container smaller, we have the same number of particles in here, but now they're much closer together. And the area of the inside of this container has become smaller, right? These particles are going to be colliding with the sides of the container more frequently, and that collective force is going to be spread out over a smaller area, and the pressure will increase.
If you have the same amount of molecules on both pistons there,
Mm-hmm.
why isn't it just the same volume?
Well, the pressure's different. So why isn't this the same volume? Because it's the same number of particles. The only way to make this volume smaller is to push down on the top.
So volume includes like that empty space too.
When you push down on the top, you force the molecules or particles to be closer together. You've essentially removed some of that empty space. It will not do this spontaneously.
So other than like, not taking into account like chemical reactions and stuff,
Mhm.
is that why like things will fall apart over time? Could that be a factor? Is just particles running into it, or because you said like one wouldn't make a difference, but if you had it constantly going, like
I think the issue of things falling apart, decay, has more to do with chemical reactions that occur. But some of those chemical reactions require oxygen. I don't know if any of you have silver flatware at home or any silver jewelry or anything, but silver tends to tarnish over time. Why does it do that? It's reacting with oxygen in the air. How is it reacting with the oxygen? Well, the oxygen molecules are moving, and when an oxygen molecule hits the surface of the silver, there's a possibility that the silver can react with the oxygen. So in that sense, yeah, this has something to do with things decaying. Yes?
So you just put like that, so you put your silverware like in like a nitrogen gas-filled box, it'll never tarnish it?
Correct. If you store your silver under nitrogen, it will not tarnish.
Could you also just keep it at a cool temperature so that there's not enough energy in the system?
There's a lot of different things. Yeah, if you store it at a cooler temperature, that would help. They sell special cloths to keep it covered that help as well, and they all function on different chemical principles. Any other questions? It could be helium. Okay, let's look at Charles' Law. Charles' Law says the volume of a gas is directly proportional to its absolute temperature. That means in kelvins. So, kinetic molecular theory says if we increase the temperature of the gas, then the average speed of the particles increases. The average kinetic energy of the particles increases. So, if we heat up a gas and the particles start moving faster, if we do not allow the container volume to change, what's going to happen to the pressure? The pressure will go up. Well, Charles' Law assumes that the pressure is constant. So how can we keep the pressure constant? We have to let the volume expand. Because the particles are moving faster, they're hitting the walls more frequently, and they're hitting the walls harder. And in order to keep the pressure the same when the force goes up, we have to make the area larger as well. Does that make sense? Avogadros Law. The volume of a gas is directly proportional to the number of gas molecules. So again, you think of a container of gas, and it's at a certain pressure, it's got a certain volume. If we put more gas molecules in, what would that do to the pressure?
Increases.
It would increase it. So to keep the same pressure, again, we have to let the volume expand. I think Avogadros Law is the one that makes the most intuitive sense. If I put more gas into the container, it's going to get bigger. The gas is going to be larger in volume. Dalton's Law of partial pressures, says that the total pressure of a gas mixture is the sum of the pressures from each individual gas. Well, the particles in a gas are so small relative to the whole volume of the gas that their size doesn't matter. It's just the number of the particles. This is also important. Particles of different masses are going to have the same average kinetic energy at a particular temperature. So if you have a really large particle, just for reference, kinetic energy is equal to 1/2 the mass times the velocity squared. So if two particles have the same kinetic energy and one has larger mass, then it must have a smaller velocity. So the large particles are moving more slowly, the smaller particles are moving faster. But when they impact the wall, if they have the same average kinetic energy, they're going to exert the same average force, because the force is also related to their mass and their velocity. So because the average kinetic energy is the same, the pressure from the collisions is the same. It doesn't matter what the gas is. So, and each gas acts independently. There's so much space, they're just going along. I'm the only gas in this container. They don't even notice the other gases. Any question? Yes?
Okay, so if you had why do you have a heavier gas compared to anything compared to hydrogen? Why wouldn't it have a bigger impact?
It's moving slow.
Because it's moving slower. So a larger gas, let's say maybe krypton. Krypton's pretty big, right? Krypton, 83, 84 grams per mole. Hydrogen, 2 grams per mole. The krypton particles are much larger, they're heavier. But in a container with the same pressure, volume, and temperature, they're going to have the same average kinetic energy. And because they have a larger mass, then their velocity is going to be smaller because of this relationship. Okay? Yes?
Just to be sure, this is section 5.8, right?
I don't know if it's 5.8. I think it is. Any other questions? What about the ideal gas law? Kinetic molecular theory predicts behavior that is consistent with observations and measurements of gases, including the ideal gas law. Scientific theory, such as the kinetic molecular theory, is the most powerful kind of scientific knowledge because it helps us to predict what's going to happen. But a model such as this is not perfect, and we know that there are some conditions under which the model doesn't work, and under which the ideal gas law doesn't work. But by looking at those conditions, it helps us to understand even more what's actually going on. So if we look at temperature and molecule velocity, so the average kinetic energy of gas molecules depends on the mass and the average velocity, and that's that equation. Kinetic energy equals 1/2 the mass times the velocity squared. And that's physics, so if you don't like that, go talk to some physicist and argue about it with him. If the gas particles have different masses, the only way they can have the same kinetic energy is to have different average velocities. Everybody okay with that? It's kind of what we were just talking about. With gases, we don't use a straight average. We use what's called the root mean square velocity, which is abbreviated URMS. It's a special type of average, and we're not going to get into why we need a special type of average or exactly what it is, but there it is. It's close to the average velocity in value. So the average kinetic energy is 1/2, I believe this is Avogadros number, times the mass times this root mean square velocity squared.
Do we need to memorize that?
You don't need to memorize this. I'll clearly indicate which equations you need to know. So when we have a gas mixture at a particular temperature, the lighter particles travel faster on average than the heavier ones. And I think there's several, I know how I can tell, 80, 81. Okay, I'm not skipping slides. Your book goes through some mathematical derivations, which are really, really cool, and some of us are interested in those and others are not interested. And so if you're interested, I encourage you to go and look at those, but I'm not going to test you on them, and I'm not going to talk about them in lecture. So we can come up with this equation where the root mean square velocity, the average velocity, is equal to the square root of 3 times the ideal gas constant times the temperature in Kelvin divided by the molar mass. In order for the units to work out, we use a value of the ideal gas constant where the units are joules per mole Kelvin. And there's actually a relationship between joules and liter atmospheres. So the units do all work out. Just take my word for it. If you're bothered by that, we can look at it after class. So 8.314 joules per mole Kelvin. This is just the ideal gas constant with different units. And the molar mass here, in order for the units to work out, this needs to be in kilograms per mole. Okay, so we can calculate the average velocity of a gas, and it's going to vary with its temperature and its molar mass. So calculate the root mean square velocity of gaseous xenon atoms at 25 degrees Celsius. So we do need that equation. Oops. This is an equation that you could see on an exam. I will probably give you the equation. It's a sad. The symbol for molar mass in kilograms per mole is this weird capital M. I don't know why they did that. So what we need here is we need the molar mass in kilograms per mole. Well, it's xenon. So we look at the periodic table, 131.3 grams per mole. And then we need to convert that to kilograms per mole. So grams on the bottom, kilograms on the top, 1 times 10 to the third down there, and 1. And so we end up with 0.1313 kilograms per mole. And the temperature needs to be in Kelvin. So the temperature here is 25 degrees Celsius. So that's a nice, slightly warm room temperature. 273.15, and we get 298 K. With the molar mass and the temperature in Kelvin, we can plug those into this equation. And so this is 3 times 8.314 joules per mole Kelvin. And if you need that, I will provide that for you on a test. 298.15 Kelvin.
Why did you do the kilograms thing?
We need kilograms per mole in order for the units to work out. Yeah. So 0.1313 kilograms per mole. And it's the square root of all of that. So when I do that on my calculator, I end up with, should have, I guess, 3 significant figures, 238. Oops. And you can look at these units and you're like, well, Okay, I see that the moles cancel, and I see that the kelvins cancel. But then I've got the square root of joules per kilogram. So I know some people are curious about this. So we've got the square root of joules divided by kilograms. Well, a joule is equal to a kilogram meters squared per second squared. And that's divided by kilograms, and it's the square root. So kilograms cancel, and then we end up with meters per second. And that's why the molar mass has to be in kilograms. So this is 238 meters per second. That's pretty fast. So that's at 25 degrees Celsius, gaseous xenon atoms. Would oxygen molecules be moving faster or slower than that at 25 degrees Celsius?
Faster.
Faster. Because their molar mass is only 32. So they're going to be moving faster. So there's the answer to your question, how fast are gas molecules moving? Any questions? This part that we're in right now is important, but we're just kind of skimming the surface of it. It's part of the course outline. We have to cover it. There could be a question or two from this stuff on the final exam, but this is not a big deal. Yes?
Are you going to watch the fight on Saturday night?
That is a random question.
Yes.
No, I'm not going to watch the fight on. Okay. Molar mass and molecular velocity. So here's a graph showing number of particles that have the indicated velocity versus the molecular velocity. And what we see is that the lighter molecules, such as hydrogen, are going to have a much broader distribution of velocities. And so hydrogen, helium, water, nitrogen, oxygen, these molecules are getting larger, right? So oxygen's larger. We see that at a given set of conditions, a given temperature, the average velocity of the oxygen is lower than that of hydrogen. But what's also important is that the distribution is different. Yes?
Is there an explanation for why they're so different in speeds?
There is an explanation. The explanation for the difference in average speeds is that root mean square velocity equation that we just looked at.
Okay. So hydrogen's just unpredictable because it's so light?
Well, it's not that it's unpredictable. I mean, we can predict the average, but the range of velocities is larger.
So it's more flexible?
I don't know the explanation off the top of my head. But I believe that this difference in distribution is part of why we need to use the root mean square velocity instead of just a simple average. When you increase the temperature of a gas sample, we also see a broadening of that distribution. So here is, doesn't say what gas, it's just, but these are three curves from the same gas, but increasing temperature from 273 to 1,000 to 2,000 Kelvin. We see that the average velocity increases, but also that the distribution spreads out. So there seems to be a correlation that at higher average velocities, you have a wider distribution than you do at lower average velocities. So it spreads out.